All right, so today we're looking at infinite functions, or sorry, infinite limits. All right, so this video will cover content for Monday and Tuesday. Okay. So we've got infinite limits. So a limit or an infinite limit happens when a function's value increases or decreases without bound near some point. So what that means is as our function, if we've got a point A here, as our function either gets really, really big at that point or really, really small at that point, meaning it either goes off towards positive infinity or it goes down towards negative infinity. Okay, that's what we call an infinite limit. Okay, these are special cases of limits that don't exist, but we indicate that they approach either negative or positive infinity. Okay, so we can give our formal definition. So if we've got some f that's defined for all x near a, okay, just the same way we've been defining our limits. If f of x grows arbitrarily large for all x sufficiently close but not equal to a, so as our x values get close to a, f of x is getting really, really large, then we write the limit as x approaches a is equal to positive infinity and say that the limit of f of x as x approaches a is infinity. If f of x is negative and grows arbitrarily large in magnitude, so that means the absolute value, as x gets close to a but not equal to, then we write the limit as x approaches a of f of x is equal to negative infinity. Okay, so we can do an example. If I've got our function here, oh, I didn't mean to do that. We want to look at, so we know that x can't equal 0. Okay, so then that's what we look at our limit. So x approaches 0 from the right, and we want to do the limit as x approaches 0 from the left. Okay, with any rational function like this, you're going to have infinite limits, and so you look at when the denominator equals 0 and take your limits around those. Okay, so the limit as x approaches 0 from the right of 1 over x is going to be equal to 1 over, and so here's the tricky thing. We can't plug 0 in, okay? We can't factor or do a conjugate, so it's of the form c over 0. Okay, and if this is the case, then what we do is we use small positive, small negative. So what that means is if I'm looking at my function, so I'm looking at x approaching 0, and I'm looking at x approaching 0 from the right. So I'm looking at all of these numbers bigger than 0. Okay, and so that's, if I have any of these, what I'm going to have is just some positive number. Okay, and so we end up with a positive 1 divided by some positive number, and that's just going to give us positive infinity. Okay, if I look at the limit as x approaches 0 from the left of 1 over x, okay, I'm going to get 1 divided by, and then I'm looking in that case at all of these values that for x is less than 0. So all of these negative values, okay, so I'm going to have 1 divided by some negative number. 1 divided by some negative number is just going to give me negative infinity. Okay, and we can see this if we graph it as x approaches 0 from the right, our function goes off towards negative or towards positive infinity. And as x approaches 0 from the left, it's going off towards negative infinity. Okay. All right, so a vertical asymptote happens when, so if x approaches a of f of x goes off towards positive or negative infinity, or one of our right-handed or left-handed limits goes off towards positive and negative infinity, then the line x equals to a is called our vertical asymptote. Okay, and they don't have to be the same thing. We could have 2 different vertical asymptotes. For this case up here, we would have a vertical asymptote of x equals 0. Okay, because we had to go off to positive infinity here and negative infinity there. So the vertical asymptote is more than likely, or most times, given or shown or graphed by this dashed line. Okay. All right, so if we're doing an example here, we look at a graph that we will say has a vertical asymptote at 2 and at 4. Okay, and so we want to look at a couple different points. So let's look at what's happening around 2. So we've got the limit as x approaches 2 from the left of our function g of x. Okay, graphically, we can see that as x approaches 2 from the left, what's our function doing? Well, it's going off towards positive infinity. Okay, and then if we look at the limit as x approaches 2 from the right of g of x, okay, as x approaches 2 from the right, our function is going off towards negative infinity. Okay, so our limit as x approaches 2 of g of x is equal, or not equal, it just does not exist. Okay, our right and left-handed limits behave the same way with in regards to if they equal, then the limit at that point is that value. So if we're looking at, for example, the limit as x approaches 4 from the left, okay, our function's going down towards negative infinity. And if we look at the limit as x approaches 4 from the right of g of x, okay, so we're coming from the right, our function's going down towards negative infinity again. So because they're equal, then the limit as x approaches 4 of g of x is equal to negative infinity. Okay, so that behaves the same way. Something to note, when we're computing the limit as x approaches a of some value, this is kind of just a putting it all together thing. When we're computing some limit like this, we first try to evaluate f of a. So we first try to just plug it in. That was our first thing we learned with limits. If plugging it in would be of the form 0 over 0, we would try factoring or conjugates, try to cancel something. If f of a is of the form c over 0, where c is not 0, then our limit is infinite. And so we use the small positive sum from negative. You have to consider the signs. Okay, something to note though. That 0 over 0 and c over 0 should never actually appear in your line of work. So if you're going, well, this limit equals this, which equals this, you should never have that this limit equals 0 over 0 or c over 0, because you can't mathematically have those. Okay, those are just forms that we use to try to figure out or classify our different techniques. Okay, so when we're doing this, let's do an example. We've got the limit as x approaches 3. So we'll do the left and the right-handed limit. So the limit as x approaches 3 from the, let's do the right first. Okay. When you're doing these, you can plug in the numerator. You'll always be able to plug in the numerator. So we'll plug in 3 and we get negative 13. Okay, we can't plug 3 into the denominator, so we have to look at the signs. Okay. So I'm looking at x at 3, or it equals to 3, so I'm looking at around that. So as x approaches 3 from the right, I'm looking at all of these values that are bigger than 3. So that means that x minus 3, if I take and subtract 3 from any of these, Okay, I'm going to get a positive number. So I'll just have some positive number. So a negative 13 divided by some positive number is going to give us negative infinity. All right, and I can do the same if I'm looking at the limit as x approaches 3 from the right, or sorry, from the left. Okay, we still get negative 13 because we're just plugging 3 into the numerator. And then we're looking at what's happening with 3. So we're looking at numbers that are less than 3. Okay. So if I can any of these and subtract 3 away from them, I'm going to get some negative number. So negative 13 divided by just some random negative number is going to be positive infinity. Okay. Now, we have to ask ourselves something cool. So there's limits at infinity and there's infinite limits. So infinite limits of what we talked about today, and they're of the form as x approaches a value of a function, it's going to equal positive or negative infinity. Infinite limits is what we'll, or limits, that's infinite limits. Limits at infinity is what we'll talk about later this week. And that's as x is approaching positive or negative infinity of our function, it's going to equal some value. And we'll talk about those in the video for